Hello students, welcome you all. In pericyclic reaction, today I will start sigmatropic rearrangement. In my previous lectures, I told you about the electrocyclic reactions and cycloaddition reactions. Now, in sigmatropic rearrangement, migration of sigma bond takes place, and this migration occurs from allylic carbon atom, and within the pi framework or within the pi system, this migration takes place. So the main point here in sigmatropic reaction or sigmatropic rearrangement, migration of sigma bond. Within the pi system or within the pi framework. Okay, so suppose if you have any pi system, so this is our pi system, then first of all, if you want to write the product of this substrate molecule, then we should do the numbering. So the numbering, the allylic carbon, that should be given number 1 always. So if this is the allylic system, we can say the allylic carbon, that should be given number 1. So here this is your allylic carbon, this is given number 1, this is 2, and this is 3. So this is your allylic chain or alkyl chain. So the another main point is about the numbering. So numbering should be done. That is, allylic carbon should be given number 1. Is given number 1. Okay, so this is another main point in this reaction. So if you will see here, then one of the part here, two parts are there in this substrate molecule. One part is the alkyl part or allylic part. So this is this part, if you will see, then this part that can be called as the allylic chain, we can say allylic chain or alkyl chain. And another part, this part is the migrating part. This is our migrating part. So what happens here? Migration of sigma bond takes place from the allylic carbon atom. So this is our allylic carbon atom, and this sigma bond migrates. So this is our sigma bond which migrate. This is the sigma bond. So this migrates how? So in presence of, as it is given the energy, either heat or light, then this pi bond, the loosely held electrons, they will get disturbed, and the cyclic shift of electron will get started. So it will go over here, and this sigma bond, it migrates from first position to the third position. So what I have given, this is numbering is given 1, 2, 3, and this migrating chain can also be numbered. This should also be numbered. Either I may give the number 1, or it may be given 1 dash like this. So this 1 dash or 1 that migrates to third position. 1 is migrating to third position, or migrating part is migrated to this unsaturated carbon atom. Or otherwise we may see that the migration occurs from saturated to the unsaturated part. So this is the saturated carbon, and migration takes place to the unsaturated carbon. Usually in many reactions in sigmatropic rearrangement, the migration takes place from saturated to the unsaturated carbon. Okay, now so what kind of shift this is? So this is from first to third. So this is 1-3 shift. This shift is called as a 1-3 shift, 1-3 migration. And how many electrons are involved in this reaction during the migration? If you will see how many electrons are involved, 2 pi electrons, and these 2 sigma electrons are involved in this reaction. So this is an example of 4 electron system, or in a 4 electron system, or 8 electron system and 12 electron, 4n electron system. This is an example of 4n electron system where n is equal to 1 here. So this is an example of 4n electron system because 4 electrons are involved in the reaction. Okay, so after migration, what we can write? We may write the product that we will get. So here you will get the double bond. This single bond is converted to double bond. This double bond is converted to single bond. And here already you have R dash. Now this R is shifted to this place, third place. So R is shifted over here. So in this reaction, the R may be either hydrogen atom, or it may be your alkyl carbon, alkyl atom, or alkyl group, we can say. It may be alkyl group. Okay, so either we may write it 1,3 hydrogen shift, or it may be called as 1,3 alkyl shift. So either it may be called as 1,3H shift, or it may be alkyl shift. If hydrogen migrates, it is called as the hydrogen shift. If alkyl group migrates, then it is called as the alkyl shift. Okay, in the same way, we may write other example. Suppose now, in this reaction, if you will see, then in presence of either heat or light, you will see in analysis. So in presence of, as it gains the energy, the cyclic shift of electron gets start. Okay, and this electron will go over here, here it will go, and this sigma bond it will migrate to at this position. So what I told you, migration of sigma bond takes place from allylic carbon within the pi system. So which is the allylic carbon atom? So allylic carbon atom, this is number 1, this can be given number 2, this is number 3, 4 and 5. So allylic carbon, that should be given number 1. And from this allylic carbon, either hydrogen may be attached or some other alkyl group may be attached. So this should also be given number 1. And this sigma bond migrates from here first to fifth. So it is called as the 1,5 hydrogen shift, or it may be called as the 1,5 alkyl shift. So the product formed, so what would the product formed over here? So this is now converted into sigma bond, single bond. This has become double bond. Now single bond, this is your double bond. And here at this fifth position, already one of the R dash was there, and this is R. So this would be the product. In the same way, we can write for 1,7, 1,9, 1,9 sigmatropic shift. We can write the example. So this is an example of 4n electron system. If I put n is equal to 1, it means 4 electrons are involved over here. How many electrons are involved over here? 2. 4 pi electrons are there, and one of the sigma bond involved in this reaction. So total 6 electrons are involved in the reaction, and this is an example of 6n electron system, or this is an example of 4n plus 2 electron system. So this is an example of 4 electron system, this is an example of 6n electron system. Now if I take 1,7 shift, 1,7 sigmatropic reaction, then that would be the example of 4n electron system. If I take 1,9 shift, if 1,9 shift is taking place, then that would be an example of 4n plus 2 electron system, and so on. Now let us see some more examples. So here such type of 1-3-1 shift is taking place. Now 3-3 sigmatropic shift may also take place. Suppose I take example. Now, so in this reaction, so first of all, before migration, what you should do, you should number this, and allylic carbon is given number 1, so this can be given number 1. This is allylic carbon, second and third. In the same way, this is also allylic carbon, 1, 2, 3. Now, as it is given energy, the pi shift will start here, and this bond will get broken down, and this will go over here. This here new bond is formed over here. So, what would be the result? Here, new sigma bond is formed. Here, new pi bond is formed. Now double is converted to single bond. This single is converted to double bond. Here we have this R. So this would be the result. So new bond is formed between 3-3. New bond is formed between 3-3. So this is an example of 3-3 sigmatropic shift. This is an example of 3-3 sigmatropic shift, and this reaction actually this occurs in presence of heat. We will see later on. Okay. And this is called as, how many electrons are involved? So 2, 2 and 2 sigma bond, 2 sigma electrons. So total 6 electrons are involved here. So this is an example of 4n plus 2 electron system. This is an example of 4n plus 2 electron system. Okay. Now, so what is the name of this reaction? This is an example of Cope rearrangement actually. So we will see later on more about this Cope rearrangement with many examples. We will see after this lecture. Now in the same way, we may write for another one, suppose so. Now what about this one? So here again, for this, allylic carbon is given number 1, this is number 2, this is number 3. Now this is oxygen atom is present at the place of allylic carbon. So this is also can be given number 1, 2, 3. And as it is given heat, the shift of electron that will take place here, this bond will break 1, 1. Here also you can see 1-1 bond break. In previous examples you have seen 1-1 bond breaks, that is sigma bond breaks, and here 3-3 bond, new 3-3 bond is formed over here. So what you may write, the here oxygen double bond that will be formed. This is the single bond, and this is our double bond. So this would be the product. So unsaturated carbonyl compound is formed in this case, and here also this is an example of 3-3 sigmatropic shift, and the name of this reaction is Claisen-Cope rearrangement. Claisen-Cope rearrangement reaction. We will also see the examples of this reaction later on. In the same way, in place of suppose this. Another example of sigmatropic reaction. Okay. Now, if you will see here, this is first. Allylic carbon is given number 1. This is second, and this is third. And the atom which is attached to this allylic carbon atom is here is oxygen. Here also atom which is attached to the allylic carbon atom is oxygen. Here atom which is attached to allylic carbon is the another carbon atom which is the allylic carbon atom, like this. So here we may also give number 1, this is number 2, and this can be given number 3. Now again, as it is given energy, the cyclic shift of electron will start, 1-1 bond will break, and here we will get 3-3 bond is formed. New 3-3 bond is formed. So this is an example of 3-3 sigmatropic rearrangement reaction. So what is formed over here? We may write. So here double bond is formed. Now the bond is formed between this one 3-3. Now this is single bond. This is our double bond. This is formed, and here already is present. This double bond is converted into single bond. One of the hydrogen is present over here, and now if you will see here, this aromatic ring is converted into non-aromatic one. This aromatic ring is converted into non-aromatic ring, so that's why it will again try to become the aromatic. For that the hydrogen is lost over here, and double bond it will become aromatic. This electron pi electron will go like this, and finally what you will find that O minus that will take this H plus, which is moved, and finally we have here this one and this ortho allyl phenol is formed in this case. So we have already read such type of reaction, and this is an example of Claisen rearrangement. And in Claisen rearrangement, the reaction takes place between aryl ether. So this is an example of aryl or allyl. We can say aryl ether. And what is this? This group is allyl group, and this group is vinyl group. So this is an example of this allyl vinyl ether. This is our allyl vinyl ether. Okay, so like this. So these are the example of 3-3 sigmatropic rearrangement. Now in next example, if you will see, 2-3 sigmatropic shift is also possible. 2-3 sigmatropic shift. So let us see 2-3 sigmatropic shift. Suppose if we have now. So in this reaction, if you will see, as it is given energy, then what will happen? So first of all, I should give the numbering. So numbering, that is allylic carbon is given number 1. So this is 1, 2, 3. Atom which is attached to allylic carbon atom, that is also given number 1. So this is 1 and this is number 2. Okay. Now as it is given energy, then shift of electron will get start, and so what is formed over here? So if you see, and this bond has broken down. 1 is broken down again, and what you have got? You have got oxygen over here, and oxygen, and then you will new bond is formed over here between this oxygen and this carbon, and if you have this one, and then this is formed like this. So this is the 2-3 sigmatropic. The bond is formed between 2 and 3. This is an example of 2-3 sigmatropic shift. Okay, so now we will see some more examples on this 2-3 sigmatropic shift or 3-3 sigmatropic shift, and so on. We will see many examples. Now before starting such reactions, let us analyze this reaction. Okay, let us see how we can analyze this reaction, under what condition this reaction will take place. Either thermal condition they are allowed, or photochemical condition, or what is the position of orbitals which interact. Either intrafacial interaction will take place or suprafacial interaction takes place here. So now analysis. First of all, we will analyze 4n electron system. let us analyze 4n electron system. So if you have, suppose 4n electron system, I am taking the example of 4n electron system where this is an allylic part, and with this allylic part one of the hydrogen is present. Now in this reaction, if you see what I have told you, allylic carbon is given number 1, this is 2, this is 3. Now what I have to see, this bond breaks, this sigma bond breaks, and it comes to the third position. What I have told you, 1-1 bond breaks, 1-1 bond breaks, and 1-3 bond is formed. So when it breaks, suppose what I see, suppose it breaks to form the sigma bond breaks to form a radical. So the sigma bond is break to form a radical. So what we can see here, this suppose bond is going to break and a radical are formed. Though what in introduction part already have told you, in pericyclic reaction there is no possibility of formation of any intermediate, like neither any this radical is formed, neither carbocation, neither carbanion, neither carbene. These intermediates are not formed in such reactions. So but here to analyze this reaction, to analyze the mechanism of this reaction, what I have taken just for the understanding, I have the radicals are written. So radicals are written over here. So let us see in terms of radical, though radicals are not formed, what I am telling you. Now in this case, suppose, so this is allyl radical. This radical is the allyl radical, and this is the H radical, or this is our H radical or hydrogen radical. Now under thermal condition, what would be the HOMO for this allyl radical? We know for allyl radical, because this is 3 carbon system, and how many electrons are there? 3 electrons are involved. 3 electrons, 3 carbon system. So allylic radical, we know that because this is a 3 electron system, a 3 carbon system, odd electron system, odd atom system. So how many molecular orbitals would be formed? 3 molecular orbitals would be formed like this. So one is plus, 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 this is psi1, and then this is our non-bonding orbital, and in non-bonding orbital one of the node is present in psi2, and this node passed through the carbon atom. Already I have given you the lecture on the how we can form the molecular orbitals for any allylic system or for any unsaturated system that I have told you. So this is minus, minus, minus we can write, and for, because this is psi2, that is even molecular orbital. So what I have told you the rule, for even molecular orbital, the end orbital that should have the opposite sign, and the one of the node for non-bonding one that passed through the carbon atom, and this is our psi3. Psi3 means end orbital is having the same sign, because this is odd molecular orbital and this is minus. So minus, plus, minus. Psi3 means 2 nodes are present. These nodes are in between the carbon atom. So because 3 electrons are present, 2 electrons over here under thermal condition, and 1 electrons over here under thermal condition. So this is our HOMO under thermal condition. What about under photochemical condition? Under photochemical condition, so this electron will get excited and it will go into the psi3 under photochemical condition. So this would be the HOMO under photochemical condition. So that's why what I may write in terms of orbital psi2, that is HOMO for this allylic radical, and it is having plus sign and one is any minus sign. And from this, suppose this is first one, this is our first carbon, this is our first carbon, second carbon and third carbon. This is first carbon, second carbon, and this is third carbon. Now another is the H radical. So H radical, this hydrogen is present over here. So this is under thermal conditions. We are discussing 4n electron system, and 4n electron system under thermal condition. Under thermal condition. Okay, so this is thermal condition. Now this bond break, this sigma bond break, and the new bond that would be formed between first and third. New bond that would be formed between first and third. And how we can write it? So that can be formed either in this way. You can see, if you see, then okay. So here this hydrogen this bond breaks and it will interact like this here. So suppose it forms a bond. It forms a bond, and this plus minus, this bond cannot form. The bond cannot be formed between plus minus. The bond can be formed between this plus and this plus. Means this hydrogen that will interact in an opposite manner now. So that is intrafacially. Okay. Firstly it was at this side. Now it will attach at this side in a product. Means intrafacially. So the hydrogen this bond breaks, and this will now interact intrafacially like this. So what kind of interaction is taking place here? The interaction is intrafacial interaction. Intrafacially interaction is taking place under thermal condition. Under thermal condition, intrafacial interaction is taking place. Now if you want to do the suprafacial, then suprafacial interaction that will not occur. The superficial, this is disallowed. Intrafacial here is allowed. Intrafacial is allowed, whereas suprafacial, if you want to do suprafacial, then that would not be allowed. This is not allowed over here. You'll see, then this would not be allowed like this. So finally what you will get? You will get this thing. Now here under superficial, superficial like this and this one. So this is bonding interaction and this is anti-bonding interaction. Anti-bonding interaction which is not allowed. Here bonding interaction. Here bonding interaction under superficial. So this is superficial, but it is not allowed. Superficial, this is disallowed. Okay. So what we may draw the conclusion. What conclusion that I may draw now? So let us write the conclusion. Okay, so what conclusion that we may draw? So what kind of shift we are studying here? The hydrogen shift. For hydrogen shift, if hydrogen is migrating, then for 4n electron system under thermal condition, shift which is possible is the intrafacial shift. Okay, this is intrafacial shift is possible. Now, so let us see for our 4n for under photochemical condition. Let us see for photochemical condition now. So if you see for photochemical condition, then and what we should write here? We should take under photochemical condition for this allylic radical, the HOMO would be psi 3. Side 3 is the HOMO under photochemical condition. Means if both, this is odd molecular orbital, that's why end orbital will have the same sign, and this is minus minus. Now hydrogen is attached over here. Okay. Now, so this sigma bond, this will break. This is our 1, this is 2, this is 3. 1 is attached. Now this sigma bond will break, and after when it will break out, and what you will get? Now and finally it breaks completely, and you will get the migration over here. Migration over here. This is migrated like this. Okay. So the migration is taking suprafacial, in a suprafacial manner from the same side. It is migrated from this side, and it is attached to the same side. So that's why it is suprafacial migration. Now if you want to do the intra, then what you can do, if you will see intrafacial, whether intrafacial is allowed? No, intrafacial, that would not be allowed. So because suppose it will go over here, and if it migrates like this, then this would not be allowed. This is not allowed because this will be attached to the minus, anti-bonding interaction that will take place. That's why this is intra is not allowed. Intra is disallowed. Only supra is allowed under photochemical condition. So under photochemical condition, only supra is allowed. So what I should write here, under photochemical condition, supra is allowed. Okay. Now, so that I have seen for this, I have given for rule for 4n electron system. In the same way, I may write for 4n plus 2 electron systems. So let us write the rule for 4n plus 2 electron system. So the rule that I will write, the rule that I will prove here, so the rule will be this one. So 4n plus 2 electron system, I will get here supra, and here I will get intra. So let us see how I will get this thing. Now 4n plus 2 electron system. Okay. So if you have 4n plus 2 electron system, then so the migration takes place from the allylic carbon atom. So better we should do the numbering first. 1 allylic carbon is given number 1. This is 2, 3, 4 and 5. Now as in presence of heat or light, as it gains the energy, cyclic shift of electron takes place, and this 1 dash, that is sigma bond, it will break and it will get shifted to the 5th position, and here we will get 1,5 shift. This shift is a 1,5 shift, and finally you will get here single bond. This is our double bond over here, and this is new double bond is formed over here, and new sigma bond is formed. So hydrogen is shifted from 1st to 5th position, 1,5 shift. It is 1,5 shift. You can write 1,5 shift. Now how we can analyze this reaction? We will analyze in a similar manner that like that of a 4n electron system. So for this, let us see, and that we may see that suppose it forms a radical. Suppose it forms a radical. This one radical and this one. This is sigma bond which breaks, the new sigma bond which is formed over here. Okay. suppose here I should write in this way. This is the product actually. This is the product actually. So I should write the breaking of this bond. First I should write the breaking of this bond, then the product will be formed. So here like this. Now under thermal condition, first let us see for under thermal condition. Under thermal condition, now so this is our two part, and one is the allylic part and there is the migrating part. So this allylic part is the pentadienyl anion. So pentadienyl anion, for pentadienyl anion we have 5 molecular orbitals. We have 5 psi1, psi2, psi3, psi4 and psi5. How many electrons are present in pentadienyl radical? 1, 3, 5, which are involved in the reaction. So 2 over here, 2 over here and 1 over here under thermal condition. Under photochemical condition, 2 over here, 2, and this will get shifted to this place. And now here in this case, under thermal condition, this will be the HOMO, that is psi3 will be the HOMO. Under photochemical condition, psi4 that would be the HOMO. Psi4 would be the HOMO under photochemical condition. Now, so I will write the HOMO for this. So HOMO for this, I may write the HOMO. If I write the HOMO, then suppose I write it this way. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, like this. End orbital for this HOMO, that is psi3. HOMO, that is psi3, that is plus sign. Now from here, suppose this is number 1, this is number 2, 3, 4 and this is 5. In the same way, this is given number 1, this is 2, this is 3, sorry, this is 1, this is 2, this is 3, 4 and 5. Okay, now from here, one of this H radical is present over here like this. Now, so this bond breaks, 1, 1, this will break, 1, 1 breaks, and what you will get? So under thermal condition, because under thermal condition, psi3 that would be the HOMO. So after breaking of this bond, that will, it means that it will attach to the 5th position. So it will migrate to the 5th position, and this migration, it may take place in what manner? It may take place in a suprafacial manner. So this migration plus interaction can occur in a suprafacial manner like this. Okay. Okay. Now, so this is our suprafacial interaction under thermal condition. So suprafacial interaction under thermal condition that we have got. Now under photochemical condition. So under photochemical condition, what would be the HOMO? So let us see for photochemical condition, H nu, second case, photochemical condition. Now HOMO that would be here, HOMO would be plus, that is psi4 that would be the HOMO, psi4 will be the HOMO, and in psi4 the end orbital will have the opposite sign. So psi4 is the HOMO, end orbital is having the opposite sign, plus and minus. Here I may write plus, here I may write minus. Now, so under photochemical condition, it will not form, it cannot migrate suprafacially, because if the migration occurs suprafacially, then the sigma bond will not get formed. So no doubt it will migrate in a intrafacial manner. So how you may write, we may show it in this way. Like this. Or finally what we may write? We may write like this. So here intrafacial interaction, intrafacial interaction. So under photochemical condition for 4n plus 2 electron system, intrafacial interaction that will take place, that we have proved over here. So here to analyze this reaction, what we have considered the formation of the radical, though radicals are not formed in pericyclic reaction. So now let us prove this one in a, and no, so this is if you see, and this is the selection rule for hydrogen shift. Now let us come for the alkyl shift. Now if you see, now we will see the selection rule for alkyl shift. Now alkyl shift. For 4n electron system we will see, as well as for 4n plus 2 electron system we will also see. Okay, now let us see how. Now for alkyl shift. For an electron system and under thermal condition first, let us see. Now if you will see, then suppose here this carbon is the allylic carbon is attached to any alkyl group, and suppose this is our alkyl group. This is our alkyl group, and this is the stereochemistry of this alkyl group. Now first of all, like before, I should give the number 1, 2, 3, and this is again this allylic, this alkyl group is given number. Now as it gains the energy, here the sigma bond, that is 1,1 bond, that will migrate and it will go over here. So shift is 1,3, but alkyl shift, but it is alkyl 1. Now when it migrate, then again consider it that a radical is formed. Though what I have told you, radicals are not formed, but I am considering that the radical are formed like this. This is the radical which is formed. Okay, now so again this is our allylic radical, this is alkyl radical. Now for allylic radical, under thermal condition, already I have told you the HOMO would be psi 2. Psi 2 is the HOMO over here. Psi 2 is the HOMO over here, and here HOMO means psi 2, and this is our plus and this is our minus. Now alkyl part. Now I should write for the alkyl part. Now so the p orbital of this alkyl that I will draw, and suppose if I draw it, then it is like this. Okay. So this is the stereo of this one. This is our minus. Now let us see the type of interaction after migration. So this is before migration, and after migration, if you will see how it will migrate, so that a bond is formed with the third carbon atom. How it migrates so that bond is formed. So no doubt this bond will break. So if this is first carbon, this is second, and this is third, and this is also first carbon. So this bond will break and it migrate to this one. So for migration, no doubt the either plus plus will form a bond or minus minus will form a bond. So if it migrates, this is plus and this is minus. If it migrates, then after migration, so I should show the formation of bond only. I should show the formation of bond. So let us see that how the bond can be formed with this, between this p orbital. So suppose if it moves in this manner. Okay, suppose it moves in this manner, then the positive will go over here, 90-degree migration, and this negative is going over here. Positive is here, negative is here. Now the bond which is in plane, it is going down after 90-degree migration. This bond which is in a wedge form and dash form, this will go up in a 90-degree manner. So this is going like this is like this. Okay, now if you will see here, then this bond, bonding interaction is taking place between these two. And finally if you will see here, then this complete bond, this will break completely and a new bond is formed. This new bond is formed. How this new bond forms? The new bond forms like this. Now this minus is interacting with this minus and plus will go down. Again, I should rotate it by 90 degree again. I will rotate it 90 degree again so that minus interact with this and plus is coming down. And here this bond which is in plane, it is rotated to 90 degree, and this bond which is in wedge or dash, it is also rotated 90 degree. So this will go over here and this will go over like this. So what you have seen after migration, 1,3 migration, after 1,3 migration, the stereo of this carbon alkyl group is changed. The stereo of this alkyl group is changed. Here the dash wedge is on the right side, here dash wedge is on the left side. So inversion of configuration has taken place. Inversion of configuration and the inversion with suprafacial. This is attached on the same side. So it was before, after. Alkyl group before and after are on the same side. So that's why it is called as suprafacial interaction. Suprafacial interaction is taking place with inversion of configuration. So better I should write in a short form SI. So suprafacial interaction with inversion of configuration under photochemical condition. So I may write the selection rule SI over here. Either SI or in another way. Suppose what I do, suppose this positive lobe which is down, it can also form bond from the upside also, from here. Here negative and here positive can form a bond with positive after migration. So suppose it goes up like this and it forms bond like this. So how it will form bond? If I rotate this one by 180 degree and it will form over here, it will go over here. And this will also, these alkyl groups, this will also get rotated by 180 degree. So after 180 degree rotation, intrafacial interaction that will take place. So intrafacial interaction after 180 degree that will take place, and if you see, then this is plus minus, this is our minus, this is plus, and this is our plus minus, and this will also undergo rotation by 180 degree. So like this here, and here if you will see, this will go like this. So either interaction is suprafacial with inversion of configuration or intrafacial with retention of configuration. Here the configuration is retention. So intrafacial with retention of configuration. So I may write in a short form AR. So the final here, the in selection rule, either under thermal condition suprafacial inversion or intrafacial retention can take place. So this is under thermal condition. Now under photochemical condition, what the thing that I can write here. So let us see for photochemical condition. So yes. Now, so second part is the under photochemical condition for 4n electron system. We are studying for 4n electron system, and under photochemical condition, so what would be the HOMO? What would be the so this is equivalent to this thing. This is okay. So I should write the orbital form for this one. So under photochemical condition, 3 electron system, that's why the HOMO that would be psi3. So HOMO would be psi3 for this one. So let us write HOMO psi3. Psi3 means positive, positive, negative, negative, and orbital should have the same sign. And this is our psi3, that is HOMO. And the interaction here that will takes place over here, that is this one. How now the bond breaking will takes place? Let us see guys. Now, so this is first, second, third, and this is carbon is also given first. One bond will break, new bond should form between 3 and 1. So if this bond breaks, then and it can interact with this. So either positive interaction or negative interaction that will take place. Suppose if positive interaction takes place, so that the bond forms, then how you will show it? We may show it. Suppose this bond breaks and it is going to form a bond with this one, this lobe. So it can form a bond like this. Okay, so this interaction we can show, and this one interaction. Okay, so here finally this bond breaks, and under photochemical condition we may show in this manner. So it will form, finally the 1,3 interaction is taking place over here, and we may write this one. Okay, so what kind of interaction? This is suprafacial interaction. Bond breaking and bond formation is taking place from the same side. So that's why it is a suprafacial, and the stereo in the product remains same like this with retention of configuration. Suprafacial with retention of configuration. We may write it suprafacial with retention of configuration. So in selection rule here we can write under thermal condition suprafacial with retention of configuration is possible. Now we may also, the negative of this can also interact with the negative of this. For this, what you will do, this will interact in this way. Now rotate it in a 180 degree so that negative and negative interaction can also form a bond, but this interaction is in an intrafacial manner. First, the bond breaking means the before the breaking of bond it was here, after the formation of bond it is here, that is in an intrafacial interaction is taking place. That is why we may write it in this manner. minus plus, and this is plus minus, and this is minus minus interaction. We have to show minus minus interaction. Now here these groups substituents will also get rotated in a 180-degree manner. So here it will go in this way. So you can see it will go like this, and this is the inversion has taken place. So this is interfacial with inversion. This is interfacial with inversion is taking place. So if interfacial interactions occur, then inversion of configuration takes place. So if interfacial, then inversion of configuration. Okay, so like this. So this is I have proved for 4n electron system. Now let us see for 4n plus 2 electron system. So I should prove for I should get the rule for, sorry, so this I should write over here. Now for 4n plus 2 electron system. Okay, now so if you will see, then under thermal condition, so if we have 4n plus 2 electron system, already I have told you the example. Okay, so this is given 1, 2, 3, 4, 5, and 1 5 shift is an example of 4n plus 2 electron system. 6 electrons are involved in this reaction, and this bond may go over here. So what another way that we may show it in another way. How? Like this. So under thermal condition, what would be the HOMO for this one? So the HOMO for this one, or we should write it in this way, in a radical manner, like this. Okay, so this is pentadienyl radical, and for pentadienyl radical, what would the HOMO? The HOMO under thermal condition, that would be Psi3. So Psi3 is the HOMO under thermal condition. It is under thermal condition. We are studying under thermal condition. So Psi3 means positive lobe, and lobe should have the positive sign. Clear? Sorry. And here we should have the alkyl radical. We have alkyl group is attached. Sorry. And in the same way here also alkyl group is attached, like this. This will migrate to the 5th position. Now alkyl group minus this way. Okay, now it will migrate. So this is Psi3 HOMO, and how it will migrate, so that it may form bond with at the 5th position. So if this is 1st, 2nd, 3rd, 4th and 5th. So we may show it so that 1 5 migration and takes place. Like this. So this migration is possible suprafacially, and you can see the bond is formed between 1st and 5th. So this will migrate and this bond will get formed, and finally you will get Okay. Like this. So this bond has taken place. This bond is formed in a superficial manner, and you may see that the stereo of this carbon atom alkyl group is same in reactant as well as in product. That's why it is superficial with retention of configuration. Superficial with retention of configuration. Now, it can also interact in an interfacial manner. How it may interact? So this negative should now interact with this negative. So then only the migration is possible. So let us rotate in a 180 degree now. So now I will rotate it in a 180 degree manner. So if I rotate it, then the subsequents, they will also rotate in a 180 degree manner, and this will go like this. So what you have seen, now interfacial interaction with inversion of configuration. So inversion of configuration, now here if you will see this bond in a plane is at right side, bond in a plane is on the left side, these dash and wedge are on the right side, and here these dash and wedge on the left side. So here interfacial interaction is also possible, but with inversion of configuration. So what I should write here, either the interaction is possible in a superficial retention or interfacial inversion. These are possible. Okay. So this is when the reaction is taking place under the thermal condition. Now if reaction takes place under the photochemical condition, then let us see. Under photochemical condition, so if you have so suppose I consider a radical are formed. So this radical and this carbon radical like this. Now under photochemical condition, what would be the HOMO for this pentadienyl radical? That would be psi 4. Psi 4, that would be the HOMO for this pentadienyl radical, and psi 4 if you write, then this would be the psi 4, means positive and negative, and orbital will have the positive negative sign, that is psi 4 here. Psi 4 is the HOMO over here. Okay, and first it is like this. This is bonded to this alkyl radical, this is bonded to this alkyl radical, and this is like this. So this is our first, second, third, fourth and fifth. Now this bond, one bond will break and this will migrate to the fifth position. Now for migration, how the bond can form? So how the negative can either interact with the negative, or the positive can interact with the positive interfacially. Negative can interact with this negative superficially, or positive can interact with this positive interfacially. Now in a superficial interaction, if you will want to understand under superficial interaction, then the interaction, for the interaction to take place, it should migrate like this with a 90 degree migration. So let us show 90 degree migration. Okay, so like this 90 degree migration, and So you can see bonding interaction. Finally this will break. And you will get complete bond is broken from this position, first position, and new bond is formed at fifth position, like this. Okay, so now again, so the bond can form with this one. Again you should rotate it by 90 degree. So when you will rotate it by 90 degree, minus interaction will take place, and here this bond which is in plane will go over here, and this bond, this dash and wedge, they will go over here. So what you are seeing now, the stereochemistry of this alkyl radical has changed over here. Stereochemistry of alkyl radical is changed over here, though the interaction is suprafacial interaction from the same side. So therefore the interaction is suprafacial with inversion of configuration. So what we may write over here in selection rule, under photochemical condition for 4n plus 2 electron system, suprafacial with inversion of configuration. Now the interaction can also take place in a antifacial manner. So for antifacial manner, what you should show from positive to positive interaction. Okay, so I may write like this. Minus plus, and this is plus minus, and now it will interact. This positive will now interact with this positive lobe. So positive lobe will interact with this positive lobe, like this, and this is minus. So the substituent will also rotate. Here these lobes are rotating in a 180 degree manner, so that positive interaction from the interfacial manner is taking place. Now this substituent will also rotate in a 180 degree manner. So here you can write like this. After rotation they will go 180 degree here, and you will get that. So either suprafacial inversion of configuration can occur, or interfacial retention of configuration. This is possible. So interfacial retention of configuration is possible. So what you have seen in this selection rule, if you will see the selection rule, then here the under thermal condition or in the diagonal this follows the same rule. Diagonally the rule is same. Diagonally this rule is same. Here also diagonally the rule is same, like this. Intra, supra, the rule. Also in electrocyclic reaction and cycloaddition reaction, you have seen that diagonally the rules remains the same. So this is about the hydrogen shift and alkyl shift. We have proved it by taking consideration of the radical consideration. Now we may also prove this sigmatropic rearrangement by 4n plus 2 by FMO method, that is frontier molecular orbital method. Now in my next lecture I will prove this sigmatropic rearrangement reaction by this frontier molecular orbital method.